Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello students, now today we will discuss about the questions answers of paragraph questions of 2014 JEE Advanced Physics Paper 2. So let us start with the paragraph type questions of 2014 and see what is the type of question they ask you in the advanced paper. So let us start with question number 31, that is paragraph question. Hello students, today let us start with the paragraph type questions. In paragraph questions, you will be given a paragraph, certain information is given, and based on the information you will be asked two questions to answer. So here there is a paragraph, you see here is a paragraph, it has some information, and based on this you have to answer question number 31 and 32. The number we ranked as starting from 1 with multiple choice questions to more than one option correct to one option correct only, and then paragraph we have numbered 1, 2, 3, 4 like so on. So therefore it is 31 and 32. That is according to us. So we have first of all we'll read the question, then we'll answer the question. See here in the figure, a container is shown to have a movable piston on top. So there is a figure not given, I'll draw for you. There is a cylinder piston system. So here is a cylinder and two compartment is there. So I have got piston over here. The container and the piston over here are all made of perfectly insulating material. So heat cannot escape. Heat energy cannot escape from here or enter here, allowing no heat transfer between outside and inside container. So there is no exchange of heat from here with the surrounding. So that heat exchange delta Q is 0. No transfer of heat because this is insulating. So I will make this insulating. Okay, this is insulating. Now the container is divided into two compartments by a rigid partition made up of thermally conducting material. There is a partition, two compartments, one is this, another is this. There are two compartments by a rigid partition made of thermally conducting material that allows slow transfer of heat. The heat will transfer from one compartment to other compartment, but this process is very slow transfer. Now the lower compartment, this one of the container, is filled with 2 moles of idle. So this compartment has 2 moles of monoatomic gas. And at temperature 700 Kelvin. This is the temperature. And the upper compartment is filled with, this is filled with another gas, and that is 2 moles, again it is 2 moles of ideal diatomic gas. This is diatomic now, and temperature is 400 Kelvin. So this is the situation that this is a cylinder which contains 2 different types of gases between the 2 compartments, and this is the boundary which separates these 2, and this is thermally insulating, not insulating. It can conduct, so it is not insulating. Heat transfer can take place between the 2, so it can transfer from this part to the other part. It can go from lower level to, or from this to that side, or that to this side, depending on the situation which is having higher heat content. Now the question is, so this contains 2 moles, this also contains 2 moles, this is diatomic, this is monoatomic, this temperature is 400, this temperature is 700. So the conduction is obviously will be from this side to that side, because it's at higher temperature. The heat capacities per mole of an ideal monoatomic gases are, for monoatomic gas, this one, the CP/Cv values are 3/2R and 5/2R, that we know. Cv is given for monoatomic, Cv is 3/2R and Cp is 5/2R. Similarly for diatomic gas, it is Cv is 5/2R and Cp is 7/2R. This is given to us. Even if it is not given, then we know that this is the formula. This is Cv, there is a formula we must know. Cv is F/2R. F is the number of degree of freedom, for monoatom is 3, so 3/2R, and Cp is 1 more R times 1 more to this, that is 2 plus R, so 2 plus 3 is 3, so 5R/2. Because Cp minus Cv, Cp is Cv plus R, so to this value if I add R, I will get this, to this value if I add 1 R, I will get this value. So based on these 2 formula, so these are they have given us. Now we will solve the question. Now what is the question? Let us see what is the question. The question is, consider the partition to be rigidly fixed. Partition is rigidly fixed so that it doesn't move. The partition, this is the partition which is rigidly fixed. This is fixed. I am fixing this first case. It's fixed. This one is fixed. So this partition will not move. And we have read that this rigid partition allows close transfer of heat and is not moving. Now in this case it is fixed. If it is fixed, then so that it doesn't move, when equilibrium is achieved, the final temperature of the gases will be. Now the situation is what? In this situation, there will be, because it's fixed, there will be transfer of heat from here to here, so there will be loss of heat here and gain of heat here. The loss of heat, because this is a higher temperature, so heat will flow from the lower compartment to the higher compartment, so there is a loss of heat in the lower compartment and gain of heat in the higher compartment. Now, so if I want to solve this one, I have to go for that the principle of heat transfer, that heat content, heat energy remains same, the heat loss is heat gain. This one I'll use. Heat loss. Now we know that the lower one will lose heat, and that is what we'll write here, that heat loss or gain, because that will write as NCP/dt. This formula is NCP delta T. In the second case, this is the case 1, heat loss will be here. I'll write equal to heat gain. So if I write 1 for this, then this is NCV delta T. I'll write 2 for this. This to 2. What I will have is the number of moles here is 2. In both the cases is 2. Cp is 7 by 2. Cp is this one I am considering the first one. I consider this as 1 and this as 2. So then for upper one is monoatomic, and monoatomic, which one is this? This is heat loss is due to the second one, so I'll use 2 here. I'll use 2 here and 1 here, because the lower one is losing heat because it is at temperature 700. So after 2, I have made this one 1 and 2. This is losing heat, so heat loss will be 2, and this is gaining heat, so it is that. The 1 is actually monoatomic, and this one is a diatomic gas. Diatomic gas is in the upper compartment. Now, so the lower one, which is monoatomic and 2 moles, and Cp is for monoatomic, given the question is for monoatomic is 5 by 2. For Cv it is this is Cv, this will be Cv 2, for 2 it is Cv, and this is Cp. This is 3 by 2 R, and delta T. Delta T is how much? Now this is losing heat, so its temperature was initially 700, and suppose that the final temperature is T, so this will be the loss of temperature. N1 is 2 in the upper compartment. Cp1 for diatomic gas is Cp is 7 by 2 R, so it is 7 by 2 R into delta T. Its temperature was 400. Now it will rise to some certain temperature T, so the difference is T minus 400. If I solve the question, then this 2 will cancel out, this R will cancel out. This is 3 into 700 minus T becomes 7 into T minus 400. Okay, now 7 into T minus 400, that is if I do that, then this is 2100 minus 3T, and this becomes 70 minus 2800. That is what we wrote the last time, and this is the one. If this goes to that side, this becomes 10T, and this becomes 2100 plus 2800, so this becomes 4900, and this is 10T. So T becomes 490 Kelvin. So the temperature comes out to be, because when the two compartments are like this and heat transfer is taking place, and this is here that screw which can be adjusted. The temperature here was initially 400 and initially 700. Now at equilibrium, the temperature is for this one it is 490, and this one is also 490. In that case, there is equal transfer, so no transfer of heat, in fact we can say, or equal heat exchange takes place. So 490 Kelvin, and if I see the option, then it is the option number 4 is correct, 490 Kelvin. Now if I move to the second part of this question, that is a paragraph. For this paragraph we have got two questions to solve, and then we have got question number 32. If I see the question number 32, what is that? It says that now consider the partition to be free. The partition to be free. The partition here is now free. It is fixed now. Now you let it go, it will be free. The partition is free, then to be free to move without friction, so that, because if you take into consider friction, then we have to consider the heat loss due to friction as well. We are saying that the heat that is transferred only to the gas and not to the walls of the container or any part of the system, only to the gas. Without friction, so that the pressure of the gases in both the compartment is same. What is same? Pressure is same. If pressure is same, it is the case of constant pressure case. Then total work done by the gases till the time they achieve equilibrium. What is the meaning of that? If the compartment is let go, then they will mix with each other. There will be movement of gases from here to that side. So there will be work done, and that can be obtained by the equation. Work done is given by, what is the work done? The work done will be given by the expression work done is nR delta T, because work done is P dV. P delta V is the work done, because pressure is constant. Because the pressure is constant, so in case of a constant pressure or isobaric process, in an isobaric process, this is the work done, and that is constant pressure and change in volume. We have ideal gas equation, which is PV equals to nRT. Then P delta V equals to nR delta T. If I differentiate this both sides of the equation, I have P dV nR delta T. So therefore, the work done is nR delta T from here. Now work done in the first case, W1 will be N1 R delta T1, N1 R delta T1, and that is we have to find that work done, and before that we have to find the final temperature when this partition is removed or is free to move. When the partition is free to move because of the pressure to move up, and as well as heat transfer will occur. So in that case I have a situation like NCP delta T again will be equal to NCP delta T In the first case it is 1 1 1 here and 2 2 2 here. Now it is what at constant pressure case, what final temperature it will achieve. Final temperature or equilibrium temperature, or that is equilibrium temperature. This is delta. If that temperature is T, say, then it is 400 was there initially at the upper compartment. It will be T minus 400 because that will increase. So it is T minus 400. T minus 400. Cp will be for the upper compartment, which is diatomic gas, and this is 7/2 R. So I'll write 7/2 R into 2 because 2 moles is there, 2 will cancel out, and here it is 2 moles, and again it is Cp for monoatomic is 5/2, so it will be 5/2 R, and that temperature will be from 700 and reduced to T. So there is a difference in temperature. So then 2 will cancel here, R will cancel here. 7 into T minus 400 becomes 5 into T. So we have 7T minus 2800, and that is 3500 minus 5T. If this comes to this side, it's 12T equals to 3500 plus 2800, which is 6300, and 12 is 6300, 30, 50 and 60, 300. Now T becomes 6300 divided by 12, and if I solve that, then I'll get 12 5s are 60, 30, 12 2s are 24, 6 0, 12 5s are, so 525. Okay. So in this situation, when the portion is movable, in that case the compartment is in Cp condition, and earlier it was in constant volume condition. So earlier it was constant volume condition, so therefore we are using Cv for that, NCVdT, but here it is NCPdT. So that is the basic difference in the question. And now if I know T, then I will go back to that equation. If I know T, I will go back to this equation to find the work done. If I want to find the work done in both the cases, first one is N1 R delta T1. I will write 2 into R into what is delta T1. Delta T1 in the first case is, suppose 1 is T minus 400, that will be 2R into 525 minus 400, so it is 125, 250R. In the second one, we'll have N2R delta T2, which is 2R. This is 2R. Delta T is 700 minus T, which is 525. This is 525 is 175. 700 T. So from 700 to T. So there is a loss of temperature, loss of heat here. Here I write 525 final temperature minus initial temperature is 700. So there will be minus 175. So this one I will write as minus here and plus here, because the difference in temperature. in terms of difference in temperature. This is a loss of temperature. So this is a minus 350 R. W1 is this, W2 is this. W1 is 250 R. So net work done is sum of the two work done. Their scalar quantity is 250 R minus 250 R, and this is minus 350 R. Minus 350 R. So it's minus 100 R. Now, if I see the option, what is the total work done or net work done, it is minus 100 R, which is option number 4. So option number 4 is correct, minus 100 R, because that in this case it is losing heat as well as this is doing work in moving the piston or the partition up. So in this case the work done is this one, which is negative, because we know that it has to spend energy, whatever energy it has, in two ways: in the rise of the temperature of the gas in the upper compartment, and also to the work done. So finally you'll get to answer this. Okay, thank you.